Can you see my screen?
Yes, please go on. Thank you.
Okay. Let me just put time here. So first, I would like to thank the organizers for the opportunity to give this talk. The title of my talk is Higher Point Functions with Hexagonalization. I start by thanking Vasco Gonçalves. He's my collaborator in the results I will show for you today. So the outline of my talk is as follows. I will start with some introduction and motivations. Then I will do a very, very short review of hexagonalization and some two particle contributions that does not appear in the octagon. Then I will mention the constraints on these objects, and I will mention the computation of the simplest 5-point function that we call the decagon. Then I will move to make some comments to even higher point correlation functions, are 6, 7, and so on. And I finish with my conclusions. So, okay, so let's go to the introduction and motivations. So as you saw in the last talk, the octagon was a big success with many very nice results. So the possible next steps in this hexagonalization maybe will be to deform the octagon. I mean, in the octagon, you take the operators to be with infinite length, and all the bridge lengths connecting these two operators are infinity. So one of what I call the deformation of the octagon will be to take one of the bridge lengths finite. And also a related problem, which has the same complexity, is to compute the 5-point function that I will give you some results of the simplest 5-point function. I have to say that at the moment, it's very difficult to get finite G results in general with hexagonalization. So we should look in general to some new resummations techniques. But anyway, it's possible to look for new structures, new constraints that this object satisfies, look to all loop relations. I will show some small progress here. And also, if somebody wants to know some no-planar integrability, these hexagons is one formulation that I think now the only one that we can learn more about this non-planar integrability. So keeping with my motivation, so I mentioned that it's possible to find new integrability expression for some Feynman integrals, very high loop Feynman integrals. So this will give some new way of understanding these integrals. And I only comment in the introduction that what is the status of computing these higher point functions. So at one loop, you can compute arbitrary any-point functions of half BPS operators in principle. That is this work by Drucker and Prefka. But at higher loops, very few results are known. There are some results for the light-like limit for 5 and 6 points. And very recently, there was a computation at strong coupling of 520 prime operators. And also, once you know the expressions for these higher point functions, it's very nice to study several interesting limits or take the light-like limit, take some OPEs to get some OPE data for non-half BPS operators and higher point functions of non-BPS operators. So there are some interesting things to analyze once you have the final result. So starting with a very, very short review of the construction. So I just mentioned that everywhere in this talk, I will be dealing with half BPS operators. I will know these operators are characterized by the position and by a non-vector. And this phi here, so they are scalar operators. So the step one of the procedure, it will start at 3-level and basically draw all the 3-level graphs. I put here example of a 4-point function of length 4 operator, and then you have all this graph here. There are many more. So this is the first step of the calculation. The line is here, the black lines are the propagators given by this expression, and the number of connections between the operators we call the bridge length. So this is the first step of the procedure. Then you go to the second step. The second step is to divide the surface into hexagon. Then promote it hexagonal path in the surface to an hexagon form factor. If the propagator does not divide the surface into hexagons, you put some additional lines that call the length zero bridge. And then the final is to cut the surface by inserting some complete set of weighted states. So for example, the octagon here, you have 4 hexagons, and then here it's when you start to put this particle, and in fact, we know that you can perform the resummation that is of these contributions. So the third step that you play basically no hole in this topic, but I just mentioned for completeness, is that there is some care to take in the boundaries of the module space, that there is a procedure called stratification. So you have to be careful because you are discretize some integration in the module space. So there is some prescription called stratification. But as I mentioned, I'm just mentioning this for completeness. So the final proposal is to, if you want to compute any point functions of half BPS operator, this is the proposal. These 8 here are the hexagons form factors. This W here are the weight factors. So, and here are all the 3 levels. And this is valid not only for planar correlators, but also for non-planar correlators. So you can work with general surface, and it's very general. So this is my very short review in this construction. So I mentioned now there is a new contribution if you want to compute the decagon or deform the octagon. That's called the 2-particle contribution. These 2-particle contributions has particles in adjacent edges. And in order to compute this object, you have to compute 3 hexagons form factors. So you decompose these objects in 3 hexagons form factors. So you have this hexagon in the left and this hexagon in the right that are trivial because it only have 1 particle. This U1 and U2 are some complete set of states. So you put like fundamental particles and also bound state particles. So you are summing a complete set of states. But then you have this middle hexagon here that is the complicated part in this construction. Basically, because these 2 particles here, they interact. So they interact if this hexagon form factor has some matrix part, and basically what appears here is the S matrix of fundamental particles, and also the bound state of S matrix, that it's a complicated object. So this hexagon here it's complicated to compute in general. So this is the complication of this construction. So okay, so I have to make just one technical remark, very short, because I will use it in the future. So there is one technical remark that if you put basically the naive bases in these hexagons, as I said, you have to put a complete base of state and perform a sum of them, you get the wrong result. So there is a prescription that you just have every time you put some scalars in these hexagons, you have to dress it with some Z marker. So this is the dressing plus that I put here. And there is also the dressing minus that you basically change all the Z powers of the scalars. So the prescription is to average between this dressing plus and this dressing minus. The explanation of these Z markers is still not know how to justify this, but it's very nice if you don't put them. Your integrand has some branch cuts, is very bad, well behaved. So when you put it, you get some very nice integrand. And so only the message here is that if you put the naive basis, it is not going to work. You have to dress these scalars with some Z markers, and then you can move it and remove it from the hexagons. There is a prescription how to do this. So, okay, so two more comments. So the dependence on the cross hatches in these constructions comes from the weight factor. The weight factor is used to glue the hexagons. They depend on the cross ratio Z and alpha. Z are the space-time cross ratio, and alpha are the space-time cross ratio that I will define for you in the next slide. And L here, L is some combinations of Lorentz generators, and R is some combinations of R charge generator. And basically, it's the weight factors give you some charge of the state you are putting putting there. So at the moment, it's very easy to generate power series with integrability. You can generate some kinds at very high loop orders. And then at the moment you can fit the results to a base of integral, but this part of the calculation, you mentioned the conclusion, it's a place that I think can be improved. So let's move on. So I will show to you some two loop results, and in the way I will give you some L loops and some O loop relations. So let's start what's going on at two loops. So I will start by defining to you my notation. So the number here inside the brackets means the loop order. The number here means the number of particles, and the numbers here is inside this means the length bridge. So here you have 0, 0, you have this object here. 1, 0, you have this object here, and 0, 1, you have this object here. So this is at two loops, this is the only two particle contributions that appear if you want to compute the simplest 5-point function. The cross ratios are defined here. So you have just 4 cross ratios. I will be working on the plane. So the 5th cross ratio is a function of these 4 cross ratios. And we also have these R charge cross ratios that I'm also defining in terms of the Y's. So, okay, so let's move to some results. So I'll give you the results for these guys. I will start with this 1, 0 and 0, 1 because they are easy. So they have a very nice structure. They are given by these 5 terms. These 5 terms, there is this function f here. So this nice structure that you compute this function have 5 different cross ratios. And this k are some integrals, 5 integrals. At one loop, they are the ladder 1 integrals. At two loop, you have the result here. So it appears some more complicated integrals. That is the ladder 2. That is the pentaladder that I will define for you in a moment. That is the double box integral, and that is also, again, the ladder 2. The nice thing that, for example, to go to one loop to two loop, you only have to change this integral here. And for some specific values of A and B that I will show to you, the same structure holds to L loop. So I will give you some L loop results in a moment. So this what you have to do is promote some integrals to higher loops. So this has a very nice structure. And notice that I only give to you the result of 1, 0, because as you're going to see, all these building blocks are extremely constrained. So for example, there is this parity invariant that basically related this 1, 0 and 0, 1, just follow immediately just by equality of these two diagrams. I'm just do some parity transformation, and this is some all loop relations between these two contributions. And just follow that the case of length 0, 0 is the same, is to have these parity transformations. So the integrals that appears at two loop, I will define them for you. I think the easiest way to understand the integrals is to look at the images here. So the orange lines are some denominators, are some propagators. And basically here you have this dashed line here for the pentaladder because it has not only the propagators, but it has some non-trivial numerators as well. So it's possible to compute these integrals, and we did, for example, in the plane that we are interested in. And so this is what will appear to loop. And now I will make some comments at L loop. As I mentioned, for specific values of this A and B, some bridge lengths, I will give you the result for one component. The general case we are still working on, but if you take the bridge length 0L, you see that basically you are changing the integral as I mentioned. You keep the same E structure, but you are changing the integral. So here you have a map between some Feynman integrals and some integrability integrand. You'll be similar as Basso-Dixon, that you have this map between integrability and some. So it's a new case that, and this is more general, that you have some map between integrability and some Feynman integrals at higher loop. So okay, so I will move to the last component. The last thing that we need is this bridge length 0 particle. So there is a much more interesting combination to study. Basically, there is this combination of one particle and two particle. It's nice to study this combination because it has this very powerful flip invariance. Basically, the result of this computation is invariant of the different ways you cut this object. Not that this is like a property of this construction, that the result should be invariant by the way you you put these extra lines of zero bridge. So this object it's very interesting to study just because of this flip invariant. So these combinations. So I will come to the results. So the results of this, you see that due to the flip invariance, you have this general solution here. Basically, it's one function evaluated at 5 different values. So to go to one function to the other, basically you map how the cross ratios change when you change this, you do this cyclic rotation. And at one loop, you give this ladder one integral, and two loop, this you give by some combinations of pentaladders, double box, and double box as well. So now I will explain to you how to use these Z markers nicely. So this is the reason why I mentioned them previously. If you take any two particle at L loop for any bridge lengths, L1 and L2, they have this R charge structure given here. It also depends on the alpha bar, but it depends in a symmetric way. So I omitted the dependence here. So it's not difficult to see that it has the general structure here. Basically, it follows in all different ways you put the particles in the hexagons. So when you can see the structure just work with fundamental particles. This is very general. And there are some all loop relations connecting these particles with different bridge lengths. So for example, for two particles, there are 4 of them. And for 3 particles, 4 particles, 5 particles, in all cases, you have several. In fact, they increase. When you start to increase the number of particles, also you start to have very list of all loop relations between these two particles. And I'll give you some example that I think it's very nice. For example, for the case at two loop, that you have bridge 0, 0, you can relate one component of the 0, 0 to one component of the 0, 1. Right? And G01 is much easier to compute from the technical side for the integrability side. If you want to compute the 01 from the integrability side, you have to expand to higher order all the hexagons building blocks like the dressing phase, the dynamical factor, and so on. So this one is much easier to compute. And in fact, this object is very high constrained by that flip invariant. So if you know just one component, you know everything. So in fact, to compute the 2-point functions, the only thing we need is this 0-1 bridge, and then you can fix everything by symmetry. So just make the computation easier. So okay, I will flash to you the derivation. I have just 5 minutes, so it's one slide derivation. Basically, the prescription for the Z markers is to average between two directions, 0, plus and minus. And basically, this amounts to changing the integrability integrand the signs of some angles and momenta. And you always see some cosines that this dot here are some integrability integrand. And basically, you recall that to increase the bridge length, you multiply by this factor in this formalism. So you just expand this quotient, got this all loop relations between particles with different grid lengths. So it'll give you the result of the decagon, a true loop. So the decagon will be a generalization of will be the simplest 5-point function. It's a generalization of the Frank's simplest 4-point function. It's in the same spirit. Basically, you have very long operators, and all the bridges here are infinite, and you are isolate the inside of the diagram from the outside of the diagram. So one technical computation is to compute these guys with integrability. You not only compute this graph here that has the same three-level structure of the simplest 5-point function, but you have to compute these other diagrams here that has some length 1 bridge. It's because this, as we see, this mirror particle contributions can change the R charge structure of the graph and give a final result that is the one we wanted. So I'll give the result. So the result is again some combinations of pentaladders, double box, and so on. So just computing these diagrams. And if you want to find the correlation functions, you'll be this d square times the unique 3-level R charge structure here. And then if you can take k to infinity. So, okay, some comments about the 4-point functions. As I mentioned, if we know just two particles, you can start to study also some 4-point functions. So consider some 4-point functions with some finite length, some finite grid length here. So you have data for these correlation functions at even at 5 loops. They are computed by other methods. So in fact, we used these 4-point functions as a check of our construction. So as you see that when we start to put some bridge lengths finite, we start to have communications between of the inside and outside of this 4-point function. And then what we have is to take our two particles and only take some of the points equal, and we check the result. And in fact, if you take L12 equals to L and G equals to 2L, you can also compute some L loop 4-point function, deformed 4-point function. So okay, so a brief comment: can you do higher points, 6, 7, and so on? So this is in progress. I hope it will appear before the end of the year. I think the answer is yes. That is the Z markers relation using a bit of data and also some powerful constraints in integrability, as this flip invariant that's relate 3 particle with 2 particles, and also this very powerful decoupling that you go down for the 3 particles for the 2 particles. So I think the answer is yes. So then I will go to my conclusions. So okay, so things that I want to do is, as I mentioned, there is a very nice map, more examples of this Basso-Dixon, that you have a map between integrability and Feynman integrals. So I'll be very happy to pin down this map in general, because then we can maybe construct very high loop order integrands for very high points. It would be very nice to try to get higher loop information, like 3 loop, 4 loop, and so on. I think the easiest way would be to do some bootstrap. Basically, you saw that there is many constraints in these two particles. Of course, it would be nice to compute these things at strong coupling, the decagon at strong coupling. Also be very nice to learn how to compute the integrability directly. There are some progress in this paper, nice progresses in these two papers here. And of course, it'd be very nice to look at the connections with other techniques like chiral algebra twist, like the quantum spectral curve, other resummations techniques. So thank you very much. And I would like to thank Serra Pileira for the support, for the financial support. Okay.
Oh, let's thank Thiago for a beautiful talk. So I see that Lance has a question. Well, Lance,
thanks for that nice talk. Can you hear me?
Yes.
Yeah. So one of the important constraints when bootstrapping might be the Steinman relations, because you have a lot of different channels. Are you planning to use those when you bootstrap?
Yeah, sure. This is one of the constraints that we are looking.
Have you already seen how it works out in the cases that you know?
It's working. It's in progress. We are trying to see it from the integrability integrand, but yeah, it's in progress. But
So
for
like
sure,
the two-loop, you have a two-loop result already. You could look at it.
Yeah, that's true. That's something we are looking.
Okay.
Thanks.
Hello, how does one ask a question?
no, you can raise your hand, but go on. Go, you can ask.
Okay, thanks. This is Burkhard. I was just gonna ask this. You have like a front of this figure which has volume though, and then you say it has to have a cyclic invariance or something like this. I mean, as a Feynman graph person, you would write a complete gauge invariant set of graphs or what, and then wonder about the property of the whole thing. Like, how can I pick a piece and say this is now cyclically invariant? But this is also in the handling handles. When you do this,
You mean this graph here?
Yeah, I mean, for me, you would have to add the backside, and when you have a charge 2, for example, there's also things where you can have a bridge length 0 in the middle with 2 particles and a third particle sitting on the edge. And then I would think the whole stuff has to satisfy some cyclic invariance.
Yeah, the whole stuff satisfies. Yeah, the whole 5-point function, simplest 5-point function satisfies. So basically this contribution here, this P00 satisfies is only to see it's because the different way to cut this object, right?
Right.
So, but also you have, for the simplest 5-point function, you have to compute all these diagrams here, and they are cyclic. Basically the 5 of them, you can make them, they are related by cyclicity. So
you essentially say, you play games on the charges and see that there's like more relations than one would like.
It's the final result. If we wrote the final result as cyclic rotation, so it's cyclicity is there.
Right. Okay. And the other point is like we observed in the paper that you can't really link this Z mark addressing statically to R, right? I mean, no progress on that in this exercise, because we did a different gamma rotation for the kinematics and we got something slightly different from what you have.
Yes.
Also, if you had
maybe that is, you mean these relations here that I mentioned, these all loop relations?
No, that I'd have to play with it to really, but it's very nice that you can do that actually. But I see what you're getting at. But no, I was asking for this Z to the half and Z to the minus a half. And I also think when you have the non-longitudinal bound sets, there would be quarter powers, no?
You have. I didn't understand the question.
Your Z prescription is not the one that we see because we do a different gamma rotation. So have you generated any understanding as to what is to be done to these Zs?
No, I agree that we did the Z markers. For example, for 2 particles, that is, as you show in your paper, it's almost unique the way you put the Z markers, because you have to kill the branch cuts of the integrand.
Right.
So yeah, there is some care with rotations you make, but in the final results should be the same if you compute.
Yeah, sure. Yeah, I mean.
Yeah. But yeah, there is some care on how to put. I don't know the physical explanation of these markers yet, so something. And also because we are only studying strings at the moment, so there are some discussion that maybe if you take more different topologies, maybe the markers prescription could be more complicated. So have also to study some more complicated topology to maybe pin down completely this Z markers prescription.
Yeah, it's unsatisfactory that one doesn't know really good. Okay, thanks.
Okay.
Thank you. I suggest that we thank Thiago once more for a beautiful talk, and let's move to the discussion. So by Ivan, and as I said in the very beginning, there are no particular rules for the discussion, so it would be great to have further comments on the previous.